Hello and welcome to Module 1, the History and Value of Systems Engineering. In this section, we will talk about describing and defining the systems engineering value. First of all, when describing a system is a set of interrelated components working together towards a common objective or purpose. In order to be a true system, the components have to have certain properties. First, the properties and behaviors of each component of the set has an effect on the properties and behavior of the set as a whole. Second, the properties and behavior of each component of the set depends on the properties and behavior of at least one other component in the set. And third, each possible subset of components has the above two properties. The components cannot be subdivided into independent subsets. If components can't do something standalone, if components could do something standalone, then they wouldn't necessarily be a system. If they weren't necessary, then they wouldn't be necessary within the system. When describing a system, the set of components constituting a system has always had some characteristic or behavioral pattern that cannot be exhibited by a subset. And a system is more than the sum of its component parts. Consider again the example of cable television, where you have to change the channel with a remote control, but you also have to integrate with a DVR player or streaming service or other system as well. All the components are in existence, but in the end, it's the end user who makes it work, and it's really not a true system from that perspective. In classification of systems, there are three different ways to look at this. First of all, there's natural versus human-made, or a combination therein. All systems are either one or the other, or a combination of the two. An example of a natural system could be a volcanic system that creates heat and lava flows and builds up a whole island all around it. A human system might be something such as a computer or an airplane or something of that nature. And something in between could be a dam or type of hydroelectric station that takes advantage of nature and human interaction. Second one is considering physical versus conceptual. Physical example would be building a car or something tangible. Conceptual could be ideas or organization structure or information, something that is very valid within the confines of systems engineering and their approach and meets all the other definitions, but may not be a tangible physical item. And a third piece would be static versus dynamic. Most things in reality are dynamic, even though many things may feel like they are static. Static means something that doesn't change. In fact, you may think a building, for example, might be static, or a bridge might be static. However, the reality is they will change as components age and experience to environmental conditions. Things like that have to be dynamic and have to be taken into account because the reality is things do change. When classifying systems, you can also look at them as closed versus open. The reality is closed systems is something where it doesn't interact with the environment, and they're truly a very rare scenario. The vast majority, in fact nearly all cases that you will run into, allow some sort of open information to flow across the boundaries as both inputs and outputs. In that case, the vast majority, if not all systems you will run into in your career will be open systems. Discrete versus continuous. The type of data that you look at in there might be one versus the other, but most likely it would be the combination of the two. For example, you might look at the bank being a part of a continuous system in the monetary components of the U.S. Treasury. However, if you go in to the doors of a bank, you would see discrete components. You might see the number of tellers. You might see the number of customers. You might see the times that they are closed or the times that the loan officers are meeting. All those things are very discrete and may be part of the whole system. And the third, deterministic versus stochastic. Deterministic means the same inputs will always get the same output. It's a very logic-based approach. If you're talking of a computer where you have input A and then do this, that would be deterministic. The majority of things are stochastic because they have to define information that changes based on each time you run the system. The book by Dennis Boyd, The Defining Systems Engineering and Boundaries, he quotes, "The single largest issue in defining a new system is where to draw the system's boundaries." Boundaries are critical because they will go towards right where you need to start and stop and need to be developed early in order for the system to be successful. The systems engineer is also primarily responsible for guiding the boundary drawing process. They may not make the final decisions, but they may propose decisions to leadership or ask the question, but ultimately they are responsible for ensuring that the decision does get made. The image that you see on this slide is an example of what was called an Adepthole Model. This is a very simple version of it for illustrative purposes. When a systems engineer looks at functions, the first thing they consider are the inputs and the outputs. In that case, the inputs flow in from the left to the center, and then outputs flow out from center to the right. Next, they look at something that controls the system, requirements, functions, constraints, and then lastly, they look at the mechanism, and that is something that allows you to accomplish the function. This slide here is an example of an Adepthole one that is much more realistic of what you might see in a real application. In this case here, this illustrates an elevator using the Adepthole model. At the top, you see things such as passenger needs, maintenance quality standards, and building regulations, the requirements flowing down from the top. On the bottom, you see passengers, elevator systems, maintenance personnel. In each of these cases here, they flow through the system, and this is a great example of the Adepthole model in action. An alternate way to look at systems is by defining components, attributes, and relationships. A component is some operating part of your system. Inputs, process, or outputs are all components. An attribute is properties or something that describes the component, and then the relationship are the links between them. So for example, in the avionics, a display or control or radio components. Those would all be components. Each of those might have different attributes, such as size, weight, power, etc. And the relationships would be how they interface and interact with each other. In understanding the value of systems engineering, you have to look at it compared to traditional design where it is not used. The reality is systems engineering is harder to see the value because if it's there and things are done right, people perceive that that was always the way that they should be without understanding the value of what systems engineering did in order to accomplish that. A paper published by INCOSE and Systems Engineering Center of Excellence compared and contrasted examples of traditional design with those using systems engineering thinking. They found that in the very upfront portion of the development process, in that system design portion, that took longer. That didn't surprise anybody, and that's been a frequent complaint of those who don't truly understand the concepts of systems engineering. The reality is what they don't understand is the downfield implications there ultimately shortened the life cycle of development and created a faster product to market. At the same time, that increased design component upfront greatly reduced risk shortly thereafter. When looking at where to incorporate systems engineering within projects, the question has to be asked how much effort should be put into systems engineering compared to that of other engineering resources. Obviously, the answer is not zero because there's value of having systems engineering. Also, just as obvious, it can't be 100% because if you have no all systems engineers and nobody driving the subcomponents of the system in there, you're not going to be successful either. Studies have routinely found that between 15 and 20% of your effort being systems engineering focused is truly what is desirable for optimal success. If you have none, you can still be successful. Just will get some results, but not optimally desirable. With just a very small focus of that, you can drive up those results, but then you start to receive diminishing returns. Interestingly enough, it's very difficult to over-engineer too much systems engineering roll into the project. If you look and get about 35 and 40%, while that's very heavy in systems engineering resources, it still gives you value, and the reality is, according to this chart, you're still doing better than if you had none altogether. While there is a diminishing return for systems engineering, the slope is much more gradual than the slope going up, giving just basic systems engineering concepts to the project. Looking at large projects in here, percentage of projects meeting cost targets, schedule targets, and objective. This was based on an MIT study on large engineering projects, such as dams, power plants, roads, etc. They found that using systems engineering reduced cost, improved schedule, and what made the project much more likely to hit targets. This slide shows a survey that was conducted by both NASA and INCOSE in trying to understand both the impact and the cost benefits of systems engineering. Their study shows that the overall impact, largely reported by in COSI and NASA showed that the benefit was higher for the use of systems engineering, and the cost benefit was also higher as well. There have been many other studies that have done throughout the years comparing the value of systems engineering, and routinely have found that increased systems engineering resources have given both improved responsiveness and higher cost value to the project. So ultimately, in conclusion, it's important to understand that system engineering effort improves development quality, and the optimal level of systems engineering effort within a project is between 15 to 20%. While this is a stake in the ground, this may vary somewhat due to industry and due to the complexity of the system involved. In some cases, 20% may be a little bit low. In other cases, 15% may be a little bit high. And lastly, the quality of the systems engineering effort matters. It's important to realize that not just adding resources, but making sure that they are the right resources with the appropriate systems engineering skills and support necessary to be successful.